we have some triangle A, B, C, and let A be a length of side BC, B the length of the side AC, and C the length of the side AB. And also let alpha is a measure of angle A, beta the measure of the angle B, and gamma the measure of the angle C. The first result, let ABC a right triangle, and beta is a right angle. Oh, sorry. C is a right angle, and gamma is equal 90 degrees. And Pythagorean theorem asserts that the square C, okay, is equal sum of squares A and B. The first result. Second, cosine theorem, and this theorem asserts in the case of arbitrary triangle the square of C is equal sum of squares of A and B minus twice product AB and product cosine of angle gamma. And third result, so-called sine theorem, asserts also in the case of arbitrary triangle that the following ratios A to sine alpha is equal ratio B to sine beta and equal ratio C to sine gamma, and is equal twice radius of this circumscribed circle. Okay, we will use these three results, and let's start and try solve first of all the following problem. A problem for some simple calculation. Problem 1. The side of the triangle is 2. The angles adjacent to it are 30 and 45 degrees. Find the other sides of the triangle. We have some side. Okay. And we have the length of side AB is equal to angle A 13 degrees, angle B is equal to 45 degrees, and AC and BC. This such problem. Let's start. Solve this problem. First of all, let's note that the measure of C is equal what? Yes, 105. Yes, it is not right triangle. How can we use this theorem to find lengths of other sides? Let's note that let's introduce the altitude of these triangles, and let's denote this side by CC prime. I recall the two very useful functions, cosine alpha and sine alpha. This function was figurated in this theorem 2 and 3, and his definition is following. Let we have the right triangle, and one of the acute angles is alpha. I recall the definition. I'm sorry. C, A and B. C is hypotenuse, and the ratio A to C is cosine, and the ratio B to C is sine. Very useful function, and we have the following simple tables, the values of this function for some angles. Angle alpha, sine alpha, cosine alpha, and 0, 30 degrees, 45 degrees, 60 degrees, 90 degrees. And we have the following values of these functions: 0, 1, half, square roots 3 divided 2, square roots of 2 divided 2, symmetric values. And let's note that using these values we can find the length of the following segments. AC1 is equal. Let's introduce some variables. Let's note the length of AC by x, for example. It's unknown. This is unknown variables. We will define its values to solve some simple equation, and let's obtain some equation. First of them, AC is equal x product x and cosine this acute angle, which is 30 degrees. Oh, I'm sorry, cosine, yes. And we have the following equality. And second, we can also to calculate CC1. CC1 is equal x multiply sine is equal x half x. The second angle 45 degrees, and we can also to calculate the another segment C, no, C, maybe C prime. Let's AC prime, CC prime. Let's draw on this board. And we have that C prime C is C B multiply cosine 45 degree. Let's note that this angle is equal 45. This angle is equal 90, 30, and this angle 60, okay, 60 degrees. And this big angle is equal 105, then this 45 degrees. And this side is equal, yes, this side is equal. And then we calculate this side CC1 x half x and C prime C is equal CC prime D is equal CC prime and equal half x. And from this equation we can express CB from C prime C. CB is equal C prime C divided cosine 45 degrees, or CC prime and substitute this expression, we obtain this segment is equal square root to the product of x square roots and divided 2. And we also the last equality, the A C prime and C, the sum lengths of A C prime and C prime B is equal to A C prime plus C prime A C prime plus C prime C is equal to, and substitute these values. X multiply this expression plus this expression, and we have x and we can find sorry C prime C is equal x1 half x, and maybe yes, maybe this this is square root. Oh, okay, and we can find the values of x. X is equal 4 divided square root 3 plus 1. Oh, okay. We obtain the one of the two values, the length of segments AC. And we can substitute these values to this formula, and we can obtain CB, other length. And this problem is solved. This problem was on the last seminars as a home task, and we obtain the solution of this simple problem. Okay, this is a simple calculation, but we teach, we learn, and I teach and you learn to solve the simple problem using these formulas, and to derive some simple calculation which use these simple formulas. Okay, and the second simple problem. Problem 2. There is enough symbol, maybe exercise, but the formulation is not interesting. The line passing through the vertex A of the square ABCD intersects the side CD at the point E. And the straight line BC at the point F. Proof that sum of inverse squares of length sides AE and AC is equal inverse square of AB. We have the following picture: A, B, C, D, and some straight line which starts it starts from vertex A and intersect the side CD in the point E, and line BC in the point F. This segment AE and this segment AF and this segment AB. And we must to prove this equality. Let's try to solve. Let's try to prove this equality. Let's note that from definition we have the follow evident corollaries, sequences of this definition. This sum of squares of this function is equal 1. And we can see on this picture the many similar triangles, enough very similar angles. This angle, this angle, this right angle, this right angle, these angles, these angles. Very many enough similar triangles, and we have many equal ratios of these sides, and we can use these ratios and obtain. We can transform this equality and, for example, obtain. We can rewrite this equality in the form, for example, a square AF square is equal AF square plus AE square is equal and one more steps and we obtain a unit in the right side, and we have the very naive idea to use this formula. Let's try to rewrite these equalities in the following form. And one more step. Let's multiply these equalities, and we obtain that this we can kill these two values, and first summands can be rewritten in the form as a ratio a b square ae square plus the second ab square divided af square. If we consider this picture, that we can know that the ratio AB to AE, AB, AB, and AE. What is this ratio? This one to this one. This is a square, and this side is equal to this side, and the ratio, this ratio is equal ratio AD to the AE, and let this angle is equal alpha. Let's know it by alpha. This note, and we obtain the ratio is equal cosine, a square cosine of alpha. And let's note the ratio AB to AF. What is the ratio? Yes, this side is legs and this side is hypotenuse. And this ratio is equal sine of this angle, but this angle is equal to this, and we obtain that this is sine alpha, square sine alpha. And the last step, using this nice formula, we obtain that this sum is equal unit 1 is equal 1. It's enough simple problem, but on first view is it seems enough hard problem, but there is a simple problem. Okay, let's consider the more hard problem exercise. This exercise was on the last lecture, and I sent this exercise by email. And okay. Can you see this picture? Yeah. A, E, this side in this right triangle, and AD this side, this adjacent side to the angle A. And in this triangle, AB is opposite side to the same angle, and this ratio in this case is sine of this angle, and in this case this ratio is cosine in this angle, and we obtain the sum of two squares, sine square and cosine square, and using this formula we obtain that is equal 1 is equal unit. Okay, understand? Okay. Let's solve the following problem. I call some definition and properties of the circle. Let we have a circle with a center in the point O, and let A some point outside the circle. I call what mean tangent straight line. This line, which has only one common point with a circle. And using simple properties of perpendicular, we easy to obtain that the radius circle, which intersect the circle and tangent line in this common point, is perpendicular to tangent straight line, because this minimal distance, the length of this segment is minimal and is equal for distance from center of circle to the tangent line. And that's all. And I can formulate the following problem. Prove that the product of the segments intercepted by a variable tangent of a circle on two parallel tangent is constant. Let's draw the picture. We have two parallel tangent line, and we have also some tangent line which And let note by point of each tangent and circle, common points of tangent lines and circle by maybe F, E, or let be the center of or the circle E, F, K maybe, and A is the point of intersection of first fixed tangent and variable tangent, and B is second point of intersection variable tangent and fixed, and second fixed tangent. And what do we prove? The product of this length and this length is a constant. By a variable tangent, prove that the product of the segments intercepted by a variable tangent for circle on two parallel lines, this and this, BE, the product of BE and AE is some constant. Can we calculate exact the meaning of this constant? Can you guess what this constant is? How calculate this constant? Maybe in the simple case. Let variable tangent is perpendicular to the both fixed parallel tangent, and in this case this angle and this angle is right angle. And let's note the main remark. Yeah, I assert that this segment is equal to this segment, and in this case this segment is equal to this segment. This segment is equal to this segment. Why? How to prove that assertion? Let's use this simple proposition, and this angle is right and this angle is right. This side is common. This side is equal to this side. And what this means? This side, this side, this side. Why? This angle is equal to this angle. Why? Why? Uh-huh. Okay, yes, 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 yes. Angle E, K is equal, yes. We have two sides. The sum of this. Example. Why we can't uh, such picture? Okay, let's exercise to prove the quality of this angle. Let's use this assertion and let's finish the solution. In this picture, we have some symmetry between this side and this side. And if to use this symmetry, this point E applying on this point E and this angle are the same. Yeah. 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 Okay. Yes. 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 Okay, and we can calculate exactly this constant. this is product of this and of this segments, and constant is equal r square. Is it exact value of this constant. And let's to prove why. We have this angle plus this angle is equal, is a straight, the sum is a straight angle. This angle is half of this. This angle is half of this. The sum of this angle and this angle is equal right angle. This angle and this, the sum of these angles is equal to right angles. And we obtain this angle is also right. And we have many similar triangles. These triangles, these triangles. And let's write some proportions. And this is radius. This is radius. Do you get the answer? No? Let's consider this angle, this triangle, and this triangle. They're similar triangle. We have the equal corresponding angles. And let's consider the following proportions. The ratio this side to this side, and this ratio is equal this side to this side. Oh, it's very nice. We can remark that segment is equal this segment, and this segment is equal this segment. Okay, let's write these proportions on the board. B key divided R is equal R divided KA, and we obtain product BK product KA is equal R square, and BK is equal AF, KA is equal BE, and either R square. we proved this assertion. Okay. Сколько мне еще времени? The following problem. The following problem. For example, let's try to solve problem 4. Through the intersection of the diagonals of trapezoid we draw a parallel to the basis. A parallel to the basis. Show that this line is divided into equal segments by the non-parallel sides. We have some trapezoid maybe A, B, C, D. And we have the diagonals of this trapezoid AC and BD, and let E the point of intersection. And we draw the parallel to the basis straight line, and this straight line has 2 points of intersection to the non-parallel sides of these trapezoids. Maybe point K, one of them, and let L the other point of intersection. We need to prove that lengths of segment KA and KE, KE is equal lengths of segments EL. Let's try to prove. Simple, simple idea. Yeah. We have the following two triangles, yes? One of them, solution. Let's consider the following triangles: ABC and triangles BDC. ABC and maybe BCD. These triangles have the common side BC common side, and we have some parallel straight line. We have three parallel straight lines. Three. Okay. Maybe right on. We get the ratio, some ratio, yeah? We can use the sales theorem. You need to use some proportions and repeat please. The side K8 BK A BKA, yes. No. I'm not sure that is right. Why? We have some similar triangles. Is it right? It's the same. And this triangle, ABC and AKE, is similar. And this triangle is similar. And we have some proportions, yes, in this triangle. And we have also some proportions. This one, the ratio this one to this one is equal to the ratio this one to this one. And this ratio this one to this one is equal to the ratio this one to this one. It's right. And We also have these triangles, also proportional. Let's write these ratios, and maybe these proportions help us to find the solution of this problem. And we have the following proportions. The ratio AK to KB is equal A. Maybe AE to BC and equal KE. AE. I'm sorry. AK. AE to AC. Maybe other proportions. AK to AB is equal KE to BC is equal AE to AC. And GL to DC is equal EL to BC. And also we use also other triangles, these triangles and these triangles. You can use this triangle, and this triangle, and this triangle. And the other, if you can use this triangle, we obtain that use this triangle. Key KB KB is equal AD and CL KLD, CL CD is equal AL KD. CL and let's deduce from this equation the assertion of this theorem and other words. We have this divided this, also this is divided also this. Maybe a more simple way. You can to add maybe this. Maybe a more simple way. Let's calculate it. AKKB with this. And this to this, it can then consider difference between these equalities. This. This, and this. Okay, it's very simple. Let's consider this also как this, and other this also как as this also this. Maybe KE, the ratio KE and ratio BC is KE, the ratio KE BC is is equal KB or KE BC, the ratio KE KB is ratio AK, the ratio AE EC, and from this KE AD KE ED AK KB. Oh wait, KB AK. I want to compare this ratio and this ratio. I want to compare this ratio and this ratio by two ways. And one of the ways, this, using this triangle, and using second triangle, this and this is equal to this. And first, KB, KK from this triangle is equal KB, KA, CE, EA. CE. And for other triangle, for other, KB, AK from other is equal BE, ED. And we compare these equalities. And using other pair of such triangles, we obtain the symmetric solutions, and we obtain from this to this, the ratio of this to this is equal the ratio of this to this, and equal this to this, and equal this to this. Okay, let's finish. That's all. Very hard for my mind.